طيب بسم الله الرحمن الرحيم. So we started talking about the internet architecture last time, and we talked about the nuts and bullets view of the internet in terms of individual components, how the physical view comes about in terms of integrating these components in the network architecture. We talked about like core network, edge network, or access network, and so on. We also talked about the service view of the internet in terms of we have hardware and we also have software which works behind the scene, and the most important aspect of this is a protocol. So we define what protocol is. Basically, it's a set of rules that govern the communication between any two intermediate devices on the internet. We talked about some service view architectures like the client-server architecture or peer-to-peer architecture. We started also talking about access networks, and we said that access networks like these access networks are the edge networks that are used to connect the end devices to the edge router, which is at the premises of the internet service provider. So this is our entry point to the internet or to the core network. And the access network gives us an entry point to this core network, okay? And we said that these access networks, they use different technologies, and we can categorize them in three different categories. One is the residential access networks, and we started talking about one example of these, and we'll continue talking about that today. Institutional access networks, where some institutions like here at Qatar University, they use some Ethernet LANs or wireless LANs or something like this to connect our end devices to the ISP, or in that case, Ooredoo core network, okay? And we have also mobile access networks, which talk about technologies like 3G, 4G, and all the terrestrial cellular technologies, and we'll talk about some of these as well. So we started talking about one example, which is the digital subscriber line. This is one of the examples for access networks for residential home networks. And we talked about the idea of DSL is that these telephone lines, there is like the motivation behind this is that we already have like infrastructure already built today for landlines, which uses the public switch telephone network. Okay, so this infrastructure exists today. Looking at the characteristics of this infrastructure in terms of physical medium, we know that these telephone lines, they are dedicated lines that connect a user at home, or the landline of the user at home, to the public switch telephone network at the service provider side, right? And these are dedicated lines. They use the concept of circuit switching, as we will talk about in a few minutes. So the idea or the motivation is that we can use this same infrastructure to connect the home network to the internet using the exact same infrastructure, okay? And for this, we use a DSL modem, okay? And the idea of this DSL modem is that it shifts the digital data that we use in our home network. It shifts this in the frequency domain, because we know that the public switch telephone network, or our voice, has a frequency characteristic from 0 hertz to 4 kilohertz, not more than that. But this line can carry more than this in terms of frequency range. So the idea is that this DSL modem will shift the data, okay? So we'll send the data in analog form and shift it in the frequency domain, okay? Above the 4 kilohertz, as we have described last time. So we have the voice is like this, from 0 to 4 kilohertz. So we have the upstream from 4 kilohertz to 50 kilohertz, and then from 50 kilohertz all the way to 1 megahertz for the downstream. So this is downstream and this is upstream. Okay, and that's why we called it asymmetric digital subscriber line, because the downstream is much wider, in which case you can support very high data rates, relatively speaking, very high data rates in the downstream more than the upstream. Okay, but both of them, as we can see, both of them are in a frequency range which is separate from the baseband or the voice. So there's no interference between the data and the voice that we use. And for that, we use the DSL modem. So the DSL modem will shift the data in the frequency domain, create this frequency spectrum, and then the splitter works as a mixer and splitter. So it's a mixer in that direction and a splitter in that direction. So it's bidirectional. Okay. So for upstream, it mixes the upstream traffic with the voice that comes from the telephone. It mixes them. Of course, mixing does not mean interfering, because they are in two different frequency domains, right? And on this way back, for the downstream, it actually replicates the downstream to the phone and to the home network, and then the DSL modem will demodulate, or in that case, will shift the downstream to the zero frequency in order for us to exchange data on the home network. So that's basically the idea of the DSL. The good thing about DSL is that it's a dedicated subscriber line, right? So the line itself, from the home network all the way to the service provider, is dedicated for one single user. Okay? So that's one good feature about this. The bad side of this is that the data rates here are limited because of the limitations of the physical medium. The telephone line itself cannot really carry high frequency, and we know that the telephone line itself has like 4 thin wires, so it cannot carry too many analog signals, and in that case the data rates are limited. I think nowadays you can go up to maybe 12 megabits per second. Higher than 8, a little bit higher than 8, but it's still, I mean, in the range of like 12 megabits per second, not more than that. And this is in the downstream. In the upstream, it's not more than 1 megabits per second by any chance. Okay, and that's a limitation on the wire itself, on the telephone line itself. So these low data rates motivates other types of service providers to come up with other technologies, which is not common in our region at all, which is what we call cable modems or cable network. And by cable network here, we mean that instead of using the landline network, we use the TV network. And this is more common in North America, in particular, because they use cable TV. The cable TV is actually, here we have sort of a similar technology, which is the, what is it called? Mosaic, yeah. It's a similar technology, more or less, except that it's a little bit different in its details. But the cable TV service providers, they have an infrastructure to distribute TV signals not through antennas and what we use here in terms of satellite and so. They use actual infrastructure network. Okay, so they build a network to send TV to the users. Okay, so this network is again composed of. So you have the service provider. So you have the service provider. So this is the service provider. And you have a network, part of the network which uses fiber all the way to a point, okay? And from this point onward, we send the TV signal to the different users through coaxial. So this access network is in fact composed of two parts. So there is one part from the service provider to a local distribution node, okay, which is usually it usually exists in a small geographical area, okay, and from that area you have a node which switches the optical signal to electric signal and send that over coaxial lines to all the users at home. Okay, so so that's an infrastructure that that existed already, at least in some countries, not here. And the idea, again, similar to what we have done for DSL, is to use that same infrastructure to provide data services or internet access to users. The exact same way that we have done for DSL. So it's the same idea, except that here, of course, in terms of physical network, the components are different. In terms of characteristics, it's fundamentally different in the sense that TV, you know, TV normally is based on broadcast, right? So you have a channel and you broadcast that to users, okay? So usually they use broadcast network here in the sense that the TV signal goes through the coaxial line and any user can listen to it. Unlike the case for landlines, right? For landlines, the line is actually dedicated for one single user, so there is no broadcast domain. There is no broadcast domain. So the TV signal inherently is broadcasted to users, right? So that's why this network, when it was built on that concept that this line is actually shared amongst usually up to 5,000 users. And there is no scalability issue in that case. Why? Because the TV signal is broadcast to all users, right? So it's one TV signal and it gets sent through the same line to all users. But in the case of telephones, you have multiple users trying to talk and use their voice to communicate. And in that case, you do need dedicated lines. So the good news for the case of the voice is that our voice is low bandwidth. Okay? So we can use thin wires and simple type of physical medium to carry the voice in a dedicated line to the service provider. For the TV signal is high bandwidth, okay? But the good thing here as well is that this TV signal is usually sent in a form of broadcast to all users. So we can use one coaxial line to feed this TV signal to thousands of users at the same time. Why am I saying that? Because that will affect the characteristics of the data access once we start using these networks as access networks as opposed to TV network or a telephone network. Once we start using this for data, now the infrastructure itself and the way it's architectured affects the performance of data transfer. Why? Because, well, instead of using these users as consumers to the TV signal, guess what? These users are data generators. These users, they have their own home network devices that tries to create data traffic that goes on this broadcast line to the service provider. So what is the problem here? The problem is that this line is shared now amongst all these users. So the good thing about TV networks is that the data rates are higher, okay? And that's what we used to listen to that in their ads, that, you know, cable TV can get you a speed of, you know, like 20 megabits per second or something like this. And that's true, except that you're not the only one who's using that network. Unlike the telephone network, okay, which uses a dedicated line, this one uses a shared coaxial. So for cable TV service, sometimes in the morning you get very high speed, and sometimes during the afternoon you get very low speed, extremely low speed. And that's because of the fact that this line is shared in the whole geographical area, sometimes between thousands of users. So even though the theoretical data rates is 20 megabits per second, but the actual data rate is quite variable, and it actually fluctuates a lot during the day, okay, because of this shared nature of the line. Is that clear? So going back, so this type of architecture uses the what we call hybrid fiber coax. This means that it uses part of it is fiber, and the other part is coax. So from the service provider to the neighborhood, they call it a neighborhood switch or a neighborhood node, okay? Or sometimes they call it a neighborhood junction, which is a coaxial type of a switch that converts the fiber light into electric signal and send it over the shared coaxial cable, okay? So this is the hybrid fiber coaxial. It's asymmetric as well. So again, we here as well, we will shift the data in terms of frequency to a range of frequency which is not used by the TV broadcasting service, right? So the TV channels, they use certain frequency, and it depends on the channel. The frequency range is different, okay? And then we use the same concept of shifting the data in the frequency domain higher so that it does not interfere with the TV frequency, okay? And again, inspired and influenced by the client-server service architecture, again, we use an asymmetric type of data rates. So we find that up to 30 megabits per second in the downstream, and only 2 megabits per second in the upstream. This is, of course, on one hand, it's higher compared to the DSL, right? DSL was like in the range of maximum 12, but this one is 30, so this is more than double. So it looks fancy and bright, right? But if you consider the fact that this is shared, okay, so the actual data rates that you will get is a lot less than that. It's much, much less than that. And in some cases, it's less than DSL. Okay? So this has to be clear. That's because of the homes share access to the router, whereas in DSL it's dedicated access. So DSL is more deterministic in terms of data rates. So when we tell you 1 megabits per second, you get actually close to 1 megabits per second. When you get a service of 10 megabits per second downstream, then you will get close to that, pretty much. Okay? Any questions? So that's how the architecture looks like. So again, you have from the the central office from the service provider. You have the cable head end, and this part is actually fiber optics. And using fiber optics means that you can carry huge amount of traffic, because the fiber optics itself, as we will talk about in a minute, fiber optic can carry very extremely high data rates, and for a very, very long distance. Okay, so that's good. And then you have this fiber node, or what we have named it the neighborhood junction, which converts the light signal that comes from the fiber to an electric signal that goes through the coaxial cable. And this, from there, it goes to all the users in a shared access fashion. And you can have here up to 5,000 users. And that's okay for TV, of course, because it's broadcast in nature. But it's not good once you use this for data. Okay? Type. Oh, okay. So we have been using DSL and, well, in cable TV service for quite some time, and we were pretty happy with it, except that, well, the variety of services that we nowadays use at home is growing. So we have TV services, now we have voice over IP, we have video on demand, we have too many services. And in some cases, these services are not influenced by the client server, in which case some of us, or maybe many of us, we started using some of the peer-to-peer services as well, in which case our home machines, they can be used in a way as servers. Okay, so the concept of asymmetric upstream and downstream is shrinking a little bit nowadays. Okay, so we have the concept of cloud computing, which means that you store data and you don't know where your data is stored. You can use cloud storage, or you can use cloud type of processing, in which case many of our machines at home might be at any point in time a server that provides service to others. In other words, you have the motivation to have higher data rates, higher than what we used to get whether using DSL or the shared access through cable TV. So that's a revolutionary approach that has started a few years back when Verizon and some service providers started to think about building an infrastructure, building as opposed to using an existing infrastructure for data access, to build an access network which is sustainable for a very long time, and for that they need to build a new infrastructure which did not exist before. And that's what we call nowadays fiber to the home, or FTTH. Okay, so fiber to the home reverses the concept of cable TV pretty much. So the fiber is now closer to the user, not closer to the service provider. So the cable TV service uses fiber close to the service provider, and then the user himself can use coaxial, which means that the data rates are limited by the coaxial cable, and that's why we get like 30 megabits per second at maximum. But fiber to the home talks about the fact that the user himself uses an optical network. So most of us now have FTTH at home, and we have what we call optical network terminator. So we see that device that Ooredoo has installed in our houses. This is what we call optical network terminator. And what this does is that it takes, of course, our home network is here. Okay, So we have wireless routers, wired routers, and so on, and all of this gets fed to the OTN. The OTN will convert this electrical signals to optical to send it through fiber optics. And similar to cable TV, here we have optical splitter / mixer. So that mixes the optical signal from multiple users. Does that really form any kind of limitation in that case, similar to cable TV? Because that's also shared amongst multiple users, right? So you have multiple users, multiple user traffic gets mixed at the optical splitter here to go to the service provider. On the way back, this optical splitter replicates the same light signal to all the users at the same time, which means that in a way this acts, you can think of it as a hub. Do you know how the hub works? This essentially works as a hub. Okay? And that's what we call passive optical network. This one. Okay? So this optical splitter is essentially a hub. Okay? So it replicates the signal. So the question now, does that cause any limitation on the amount of traffic that comes from the user? Well, theoretically it does, but is that really a limitation? No, because the fiber optics can carry huge amount of traffic. One single cable of fiber optic can carry the traffic of few continents, not just countries. Okay, theoretically. I've read an article like way in the past, that the theoretical rates for a fiber optics, for one cable of fiber optic, which uses the light signal, can go up to 100 terabits per second, which can carry the traffic of the entire internet in one cable, pretty much. But the problem here is not the fiber optic itself. The problem is how you deal with the light signal. It's very, very complicated and sophisticated to keep the signal in the light domain all the time. Why? Because, well, just think about it. How can you switch light signals? Do you know how they switch light signals? In the optical domain. Using mirrors. They use actual mirrors. Mirror. Well, the problem is that if I use any electric device in the middle, it defeats the purpose, right? Because it will convert a light signal to electric signal, and it processes the signal in the electrical domain, and then it converts the electrical signal to light signal. And the limitation will be in the processing power of that device, right? So it defeats the purpose of using fiber optics, because the rates will drop from like 1 terabits per second all the way to 1 gigabit and all these rates that we hear about nowadays. Okay? So if we want to really achieve this terabits per second traffic, we have to keep the signal in the optical domain all the time. And the problem is that to keep this signal in the optical domain, you need very, very sophisticated devices. Okay? And you cannot really switch optical signals easily. You cannot send it like here. This the difference between passive optical network and active optical networks is exactly what I talked about. This active optical networks uses here a switch. And what this switch does is that it converts the optical signal into electrical signal, read the the actual content of the data and switch the data according to the address. And that, of course, limits data rates quite a bit. But this is active in the sense that it does not replicate the signal. It sends the signal to the right user based on the address, which is what we use in switched Ethernet. In switched Ethernet, instead of using a hub, we use a switch. And a switch does that. The switch does that. The switch will read the physical address and will send the packet content or the frame to the user based on this physical address. So that's what happens in active optical network. But in doing this, we actually lower the data rates quite a bit, because we have to, in order for us to process the content of the data, we have to convert it to the electrical domain. We cannot process an optical signal. That's not possible. Okay, is that clear? Okay. But, of course, as we said, there's no limitation in terms of traffic, especially in the passive optical networks. It uses very high data rates, and mixing the data from multiple users in that case will not form any limitation, because the data is always in the optical domain, and in optical domain you can use very, very high data rates, and the optical fiber will allow you to send very high data rates for very, very long distance. Okay, in some cases kilometers, few kilometers, okay, in distance. So once you send this to the central office, there is an optical line termination device, which again converts the aggregate traffic in that case, the aggregate signal from all the users, to switch it to the electrical domain and then send it to the core network at the service provider site. Okay, so from then on, you go to the core network, which is, well, it depends whether the service provider uses an optical core or routers and switches, in which case you will read the content of the packet and then you can route it and do whatever you want. Okay, so the idea here is that when we push the fiber optics closer to the house, we will then create a sustainable access network which can carry variety of traffic from different services from the home network to the core network. Okay, but this is an infrastructure that was built specifically for this purpose. Okay, but using this fiber to the home, we can then support all types of services. Okay, like we can use this for voice over IP, we can use this for TV, we can use this for data, we can use it for everything. And that's why nowadays people stopped or started not to use landlines. We see it's very common nowadays that people, they don't bother having a landline at home. They use their cell phone and they use TV over, and they don't even have satellites, or they don't even have antennas at home. They always use the mosaic or something like this, and they use this type of network for all types of services that they might have. And there's no actual limitation in terms of data rates. Okay, so these are the three types of residential access networks. We talked about DSL, we talked about cable TV service, and then we talked about fiber to the home. Okay, for institutional access networks, we have, of course, the predominant technology here is Ethernet. Okay, so Ethernet uses a set of switches or hubs, but of course hubs are obsolete, and You connect all the devices in your institution or organization. You connect it to a set of switches, and then you use some institutional router to connect the Ethernet LAN to the ISP core network. And these are usually leased lines, okay, which the organization rents from the service provider. And these are usually high data rates. They don't use DSL. They don't use, they may use actually some technologies like fiber, or they can use like some leased lines from the institution directly to the service provider. And through that, you can have agreements with the service provider to have data rates as you like. Of course, the Ethernet cable itself physically can carry maybe up to 100 gigabits per second, unlike the telephone line. Okay, so the like UTP or STP, you have like STP Cat 6A or something like this. It can carry up to 100 gigabits per second. Okay, so you can have very high data rates between the router at the institution and the router at the service provider. The typical data rates here are 100 megabits per second all the way to 10 gigabits per second. Okay, and of course using switches, if you're familiar with the function of the switch acts as a mixer on one side and a switch on the other side, which means that the traffic that goes from here to the users, the switch will store it, will process the packet, will read the physical address of the frame, and based on that, it sends it to the relevant end device. In which case that there's no actual contention or collision that happens between these signals. You can have all these users send at the same time, and the switch will resolve everything and will process everything as they come. And there is no actual collision here, as we will mention later on. So any question here? So of course okay. I don't think we lost anything, but let's hope. You have HSDPA, which is an evolution of GSM. And GSM, as we might know, GSM is a standard that was originally developed in Europe, versus AVDO, which is an evolution of what CDMA 2000, and this is the same line of standards that competes with GSM technologies, and this was designed originally by the US. The entire US, they always like to be different, so they have their own line, and they stick with it, and they try to force it on everyone on Earth. You have these two lines. Of course, GSM types of technologies are much wider spread compared to CDMA 2000. It's more commonly used, and that's why people started to use HSDPA, and later on we evolved that to what we use nowadays as LTE, okay, or long-term evolution. So LTE is the early start of 4G, and then LTE advanced is the 4G and so on. So all these technologies, or طبعا WiMAX, but WiMAX is almost dead now, is dying and is losing the ground to LTE. So LTE and HSDPA and HSPA and all these standards, which is evolved from GSM, these are the trend that people use nowadays. In any case, all these standards, they are used for broadband mobile wireless access, which can be used in our devices to connect our end devices to, again, the telco office or to the service provider through very wide range communication. Okay, and of course in that case, there are some limitation in terms of data rates because of the long range, and there is some limitation in terms of even the energy spent for transmission and so on. But it's one of the technologies for access networks. Okay, okay. So you have, so twisted pair means that you have first like small wires, very thin wires like this. You have number of these in one package, right? And usually these wires you get every two, and you sort of pair it together. You just like twist it. So you create like something like this. You twist these wires, and you get each pair, and you twist it like this. Each of these wires, by the way, carries separate signal in the baseband. By mixing these signals together, you can have high rates of data transfer. And some of these signals are used in one direction, the others are used in other directions, so you can use this for bidirectional. So, so this twisted pair, if you use like two pairs of these like this is a telephone line. If you use multiple of these, you can have what we call nowadays UTP or UTP Cat5, which is what we normally use for Ethernet. Okay. So UTP Cat5 can carry 100 megabits per second, and in some cases maybe close to 1 gigabits per second. And there is UTP Cat6, which carries even higher data rates. And Cat3 here, which is the telephone lines, as we said, it's close to 10 or maybe 12 megabits per second, not more than that. Okay, so that's one example for guided media. Some characteristics about this twisted pair. By twisted pair, we mean we get each pair of wires and we twist them together. Does anyone know why this twisting? To do what in the interference exactly? Interference, but there is an interference. There is internal interference and there is external interference. Internal, yeah. So internal interference is interference from other wires in the same cable. External interference talks about interference that comes from the environment. Okay? So twisting addresses the internal interference. Okay? To control the internal interference. Why? Because if you for
I'm not sure, but is it something about the magnetic field that
yes, it's related to something related to what happens is that if you don't do the twisting, you use the wires like horizontal and parallel like this, right? So chances are the amount of interference from the other wires here will be different from here. Okay? So you don't want the interference to be uneven. By twisting, you make the interference sort of even on both wires. Okay? Because you cannot say one wire is above the other, right? Because they are twisted. So the interference, if it happens, it's evened out throughout the whole wire. Okay, which is a good feature. Okay, and then the outside interference is controlled by another plastic insulation, which is what we see. We don't see these wires, right? When we see one cable, and there is a plastic jacket that insulates all the wires inside and protected from the interference that comes from the environment. So there is internal interference and outside interference. Anyway, so this is one. The other feature is that because of the fact that these wires are very thin, the signal cannot really travel for a very, very long distance unless you use very high power. So depending on the power that you use for transmission, usually the typical distance is around, the maximum distance is around 100 meters, not more than that. Okay? This is the maximum. Okay? If you want to span the network for a longer distance, what do you do? What do you have to do? You have to use what? You have to use any intermediate device, whether a repeater, or a hub, a switch, anything. That gives you another 100 meters. Okay? So when we see a UTP, all of a sudden we know that we have an indication about the distance. We have an indication about the range of data rates we're talking about. Right? So these are very important things that we keep in mind. So easier. So there are some levels. So you can support high data rates by only changing the software of the network. Well, the service provider will be attracted to do that. But usually, you will not get huge gain by replacing only software. You're not going to get that. Okay? So you can go from probably HSDPA to HSPA or to a little bit incremental gain in terms of data rates by just upgrading the software, upgrading the drivers or the software of the devices. That could be done, but usually the gain will not be that high. If you want to get really high data rates, then you have to change hardware. If you want to get extremely high data rates, you might have to change the physical medium. Okay? So it depends. But this is built from scratch, so you have the flexibility to use
so
it.
you are telling that we are using fiber, which is very expensive, especially in the terminals, instead of Ethernet cables that could cost much cheaper, just because we are thinking of tomorrow.
Well, no. Remember. In terms of cost, it's not as huge as you might think. Because remember, it's only from the home to a neighborhood switch. You're using like fiber, and then you switch everything on one fiber cable. So in terms of cost, since you are building this infrastructure from scratch, in terms of cost, it's not that big of a difference in terms of cost, because as the technologies evolve, the cost of the hardware gets cheaper and cheaper. So the fiber optics, actually the problem with fiber optics is not the cost as it is for how to handle fiber optics. Because of the bending might actually break the cable itself. So fiber optics has some special way of handling, as opposed to UTP and STP, which is very easy to handle. So you can get the cable, you can bend it, you can actually go around like objects, and there's no problem. But fibers, you have to be very careful. Okay? So in terms of infrastructure, if you look at it, from a neighborhood which spans a huge amount of users, you go into one switch or one fiber node, and then from that fiber node you have only one cable to the service provider. So you can cover districts with one cable. So it's still feasible in terms of cost. So the cost is not that major difference. Okay? It's the devices and how they are designed, whether you use passive optical device or active optical device, and the difference in terms of characteristics and the limitations of each one. Okay, so we'll break here for prayers, and we'll have a 15-minute break, and then we'll go back. Okay, continuing the discussion. as we said, the physical medium is responsible for conveying or transmitting the digital data. But before you transmit the digital data, our digital data is, it will be in a form of bits, right? Okay. We cannot transfer these bits over the physical medium. What do we have to do? We have to convert these bits into signals. Okay. So we can convert this into a digital signal or analog signal. We call this digital signal baseband. Baseband signal. This, we call it broadband. Okay. The difference between the two is as follows. So these bits can be converted into a digital signal, like simply we can say, in this will be converted into 0 will be 0 volt, and then 0, and then 1, and then 0, and then 1, and so on. Digital signal, very, very simple. This digital signal, however, is very hard to generate using physical devices. So we sometimes use some approximation. So we convert it into like some discrete or some discrete frequency signals, or what we call sine waves or cosine waves or something like this. So we approximate this like if we were to use the something like this as a signal. So the 0 will be minus voltage, and the 1 will be positive voltage. You are free to use whatever signaling you want. So we can convert this using like some type of some frequency signal or something like this, some sine wave. We approximate this to sine wave and then we transmit. This is what we call baseband transmission. Baseband transmission, we send the signal in a low frequency, in the low frequency components, without having to modulate, which means pushing the signal in the frequency domain. Okay, the analog signal uses some kind of analog representation of this signal. So, for example, the 0 will be the 0 مثلا will be مثلا signal like this, and then the 1 will be a signal like this. Different frequency or something like that. So, in other words, the frequency components in this signal will have very high variations. When you start studying this in the frequency domain, you will have like higher frequency components, something like this, because this has high frequency. Yani this is a quick introduction just to so you appreciate or you try to distinguish between a digital signal and an analog signal, and how we use each of them to represent the digital data or the actual data. Why am I saying that? Because depending on the physical medium, sometimes you are restricted to use baseband signal or digital signal, or broadband signal, or analog signal. So, for example, one example that we talked about, DSL. DSL uses baseband for voice, but it uses broadband for data, because you have to shift data in the analog domain, in the frequency domain, in the high frequency range. So you use broadband signals to represent actual data. So you have to do something like this to push data in the frequency. Okay. Ethernet uses baseband. Why? We will see in a minute why Ethernet uses baseband, and there's no need for analog signals or broadband signals. Okay. Wireless uses what? What do What do you guess?
Approved.
Annabelle. برافو عليك صح. Why?
So it has to push it in the frequency domain.
Why? صح مظبوط بس why?
For the receivers, because they listen to a specific frequency domain, basically.
Okay. Yeah. Okay. The other thing is that I want to control the interference, because if I send baseband, if everybody sends in the baseband, what will happen? Because we use air, right? Everybody will send on the baseband, which means everybody will send in the low frequency. So everything will interfere with everything. صح? In order for us to distinguish between, for example, 2.4 gigahertz and 5 gigahertz and 800 megahertz for GSM مثلا or something like this, we have to distribute the spectrum amongst the different technologies and users so that there will be some controlled interference between each technology. Because we use one single medium for everybody, right? So we have to control the spectrum. So, having said that, these bits can transmit over the wire in the baseband or in broadband, right? In the low frequency or in high frequency. The physical medium itself provides the conveyor or the vehicle that takes these bits in the baseband or in broadband from one transmitter to a receiver or to a group of receivers. In that case, these physical media are categorized into two major categories. There is the guided media, and by guided media we mean that the signal will go into a specific direction or a specific physical medium. For example, if you send a signal over a wire, it's guided because it goes through that wire. As opposed to unguided means that it goes into all directions like wireless. So wireless is by in nature unguided, unless what? Except
beams. Beams.
Except beams ماشي, except like beams يعني you're talking about optical beams مثلا? Wireless optical beams, yeah, that could be, yeah. Or microwave links, or using directional antennas or something like this. So sometimes even the wireless signal can be guided, and the wired are usually guided, right? I'm not aware of any wired that uses unguided media. So always wired means that the signal goes into the wire, which means that the signal is contained within that wire and it goes through that wire. Okay? But wireless can be guided or unguided, depending on what technologies we're talking about. Mostly, wireless is unguided. Okay? Type. So signals propagate in solid media in the case of guided media like copper or fiber or coaxial. So we need to know the difference between each type of these. Unguided talks about propagates freely like radio. And by radio we mean all types of radio, whether it's Bluetooth, Wi-Fi, cellular, anything. Okay. So we'll take one example of each. So for guided media, we talk about twisted pair. By twisted pair, we mean that we use copper wires to send the signals. So for this, we have two types of twisted pair. Of course, there are more than two types, but there are two types in this slide, which is Cat3. Cat3 refers to the telephone wires, the wires that we use for telephone lines. And for this, you see the number of wires is less. the wire itself is thinner, and the number of small wires, because twisted pair means what? Twisted pair means that you have group. Let's remove that. Oops. Coaxial cable is another example of guided media, and coaxial cable talks about one copper line. As we see here, it's one copper line and another copper shielding around it. Okay, so these are not parallel lines or twisted wires. These are concentric wires. Okay, so there's one copper line which is thick, and there is one copper shield above it. Okay, so based on this shape, the same copper line can be used for bidirectional. How? How can we use the copper line for bidirectional? Because we said for UTP we can easily use wires for one direction and other wires for one direction, and that's it, right? So can we use the same wire for bidirectional? Right, so we can use what we call frequency division duplex, or we can divide, as we did for DSL. For DSL, we use different frequency range for upstream and downstream, right? So here as well, we can use frequency division duplex for upstream and downstream for each direction. So even though it's the same line, but we can use the same line for bidirectional communication. Because of the fact that this is thicker and because of the physical characteristics, the coaxial cable can span in terms of distance maybe 5 times the UTP. So it can get maybe like 500 meters. Okay. And in terms of data rates, it's much, it can support higher data rates. As we said, for cable TV, it can span all the way to like 30 megabits per second or something like this. Or actually much larger than this. I mean, theoretically, in the gigabits per second. Okay. So it's mostly used for, it can be used for, baseband or broadband. So for baseband, so the discussion that we discussed at the beginning was preparing you for this. So when we see broadband or baseband, we know the difference between the two. So for baseband, we use it like, for example, for TV signal transmission. Or legacy Ethernet. Legacy Ethernet used to use coaxial. Of course, not in your days, but very, very long in the past. People used to use Ethernet using coaxial cables without any hubs or switches. So, so what happens is that you can actually use coaxial, and then each node or each workstation will use some kind of a T connector to connect itself to the coaxial. And then you go from one machine to another and so on. So these are T connectors that you can connect all the coaxial cables in a chain-like fashion. Of course, this kind of, Ethernet has disappeared completely by the existence of hubs and switches. So we don't have this anymore. So this is very obsolete now. For broadband, of course, we use it for TV broadcast and for even data services over coaxial cables for the case of hybrid fiber coaxial, the one that we just talked about a few minutes ago regarding providing data services over cable TV. Okay, so broadband talks about the fact that you have to distinguish the TV channels and the data services based on certain or different frequency ranges. Okay. Fiber optic cable, of course, is a glass of fiber, which is again another third example for guided media. But in this case, the signal that we're talking about, of course, in coaxial and copper, we talk about electrical signal. Okay? Here we talk about an optical signal. So the optical signal goes into the fiber optics cable, and again, the fiber optic cable is one single glass cable, which is shielded and protected again from not only interference in that case, but it's protected against breaking and against bending. Okay. The good thing about fiber optic cables is that the amount of bandwidth that it can carry is huge bandwidth, and therefore you have huge amount of data rates that you can send over the fiber optics. The fiber optic glass itself has two types. Does anyone know the two types of these glasses? There is the single mode fiber and there is multi-mode fiber. The difference is is that the multi-mode fiber, the light signal itself tends to deflect and turns to have multiple copies of the same light beam, versus the single mode talks about one single beam from the beginning of the cable all the way to the end. And that's very sophisticated and very expensive. This one is very expensive. Why? Because it requires very sophisticated light sources, like laser sources, similar to laser. So it's one single beam that goes from the beginning of the cable all the way to the end. Versus multi-mode, the light beam itself is thick, and it can diffuse the energy of the light itself and create multiple copies. And in that case, the distance that these cables can span is much less compared to single mode. Why? Because for single mode, you are concentrating the whole power in one direction. When you concentrate the whole power of the signal in one direction, then you can go very large distance. منطقي, صح? Versus if this power dissipates in multiple directions, then you get the signal attenuated, and therefore the signal cannot travel for very, very long distances. So for multi-mode fiber, the distance is around probably maybe 2 kilometers, something like this, versus single mode fibers, it can get to all the way to 100 kilometers. And that's why they use single mode fiber for what? For submarine cables. So you can go under the ocean, under the sea. One cable can go under the sea to carry the traffic of the entire continent over one or two of these wires to the internet. Okay? Anything that's not clear? Anything?
Is there going to be a sort of repeater to repeat the signal after like when it's on?
Very good point. Very good point. When we say a submarine cable, of course, we talk about more than 100 kilometers or 2 kilometers, of course. And typically, of course, they use special types of repeaters for optical fibers. So yes, so the answer is yes, definitely. Okay.
Which slows down the signal.
If you have to convert it to the electrical domain. That's why I said special types of repeaters. Special type of repeaters that they only magnify the signal without processing that. You don't need to process the signal. You need to process the signal only if you need to switch it or redirect it to a specific direction, right? like if you want to use a router or a switch. But submarine cable, you only need to move the entire signal from one place to another, point to point, right? So you don't need to switch the signal or send it anywhere. It's one point to one point. So in which case, you only need a repeater. A repeater, what it does is that in the analog domain, it just magnifies the signal. So instead of having, so the signal, when it travels through the distance, so it goes like high, very high power, and then it starts to lose power. It attenuates. So what the repeater does is that it takes the signal in this exact same analog domain without converting into the into the electrical domain, and then it magnifies the signal again. So it can go for another 100 kilometers. And then after 100 kilometers, you go again and again and again, all the way to the end.
It amplifies it with its own noise. So after some steps of amplifying it, we have to decode it to be able to send it again to reduce the noise. Because if
you don't actually decode it until the very end. Why do you need to decode it? You only need to decode it if you want to use it to switch the signal or to route based on the content of the packet. And I don't want to read the packet. I don't want to, and I'm in the physical layer. Yani from here all the way to the end of the ocean, I'm in the physical layer. I don't need to switch. I only need to switch to MAC layer or higher layers only if I want to process the content of the frame or the content of the packet in order to do switching or to do routing. Okay? But you have, like submarine cables, you have the ocean like this. Here, you want to have one cable that goes all the way. So if this is like 1,000 kilometer, مثلا, you need to put repeaters in different places for the exact same signal and magnify it all the way.
Yeah, but if you amplify the vertical noise, you will amplify also the noise of
the noise, yeah.
Noise from each,
Right.
from each node.
Right. Right. That's a good point. Remember, you amplify the noise if we're talking about wireless. Here, we're talking about a guided medium. A guided medium. Of course, if you amplify, you have the noise, right? صح. If you amplify the signal, you amplify the noise. But the assumption here is that in a guided medium, the noise is almost negligible. So even if you magnify, of course, like after thousands and thousands of kilometers, you keep magnifying the noise, but the noise itself is negligible. In guided medium, the noise is negligible. But this point is very interesting because I can narrate a very nice story when the guy from Iridi came to my house to set up the home network. So he set up the routers and things like that. So I told him, I need another point upstairs. And I have 3 stories, so I need at least one point in upstairs so that I can reach to the other 3rd floor. So he said, no, I'm not allowed to do this. You can use, they call it what? They call it repeater or something, wireless repeater. Okay? So he said that, no, we don't do that. If you want to do it, you can use repeater. So I told him, look, you're talking to a teacher in communication. Okay, so you don't tell me that this is going to work because it doesn't. I know it doesn't. Why? The idea here is that in a residential area, if you use a repeater, okay, you will magnify not only your signal, you will magnify your signal and your neighbor's signal. Right? Your neighbor's signal will form a very high noise. If you magnify this, and people have done this a lot, they go and buy these repeaters from Carrefour and stuff, and they set it up, and it doesn't work. Why? All of a sudden, they find that the performance really, really bad. Why? Because you magnify your signal and your neighbor's signal and your neighbor's signal, right? So at the end, What you get upstairs is a composite signal of your actual signal and all your neighbors' signals. So the receiver upstairs will not be able to decode the signal. Unless your neighbors are in a silence mode. Only then the interference is very, very low, and your receiver upstairs can decode the signal. But here we're talking about guided medium, and remember that the interference from the environment is almost zero. So even if you magnify the noise is unless of course we're talking about impulse noise, like if you have a tsunami or something like this, that's another story. But usually the interference in that case is almost negligible. But in wireless, this is perfectly valid. It happens a lot. Okay. So radio, that's when things become complicated. For radio, it's one medium. It's actually air. We all share it, whether you accept it or not. It's one physical medium that we all share it. Okay, so we have to arrange things in a very complicated way, and that's why in most of the cases, even in microwave links and stuff, you do have to have some broadband communication. You do have to have some analog transmission. You need to have modulation. You need to send in a specific frequency range. So baseband transmission is not valid in the case of wireless. You have to have broadband. Okay. Another thing that affects radio is all types of wireless signal impairments. When you send a wireless signal through the air, chances are there are some obstacles like this. Each obstacle has different characteristics. Each material has different characteristics with respect to the wireless signal, in the sense that it reflects the wireless signal, and some of them they reflect, some of them they diffract, some of them they create different formations of the wireless signal. So the receiver, in fact, gets different copies of the wireless signal depending on the obstacles. So you have one source that tries to send to a receiver. So the source sends a wireless signal which actually gets broadcast in the air. And then part of the energy of this signal gets propagated in a straight line. Part of it gets propagated this way and propagated this way. Okay, so this specific parts of the energy, they get sometimes reflected through different objects. Okay, and all these copies will reflect, and then the receiver here will receive multiple copies of the signal. So the signal is like this. The receiver will receive actually a signal that looks like this. Some of them are attenuated. Some of them are shifted in the time domain. Some of them are both shifted and attenuated. Okay. So you get actually a very composite signal. Okay. So the receiver here has to use special filters with special noise cancellation effects, different techniques to decode this signal and convert it into the digital bits that we can use. Okay. So radio can take the form of terrestrial microwave band in the like for example broadband wireless communication, like all types of GSM, WiMAX, and CDMA 2000 and all these, and they use different carrier frequencies, and they use bandwidths per channel, which can span all the way from few kilohertz all the way to 45 mega bits per second, or 45 megahertz. So the channels that are formed in terrestrial communication can vary depending on so many things. ماشي? For broadband communication. For Wi-Fi, the data rates are from 11 megabits per second in the B standards, and 54 in the G standards. And nowadays we have the common. The common is what? N. Bravo عليك. So the common is N. N can get hundreds of megabits per second, maybe 200 to 300 megabits per second. And the N uses both 2.4 and 5 gigahertz. It uses both. Okay. Wide area, like for 3G, again, you start from 1 megabits per second. Nowadays we have 4G, which again gets very close to 300 megabits per second. Okay. Of course, satellite communication is another is a totally different domain. Satellite, we talk about communication from the satellites to the end devices directly. So we use the satellite similar to an access point. And we used to have even internet access through satellites at some point. So satellite provides also another type of access network. And usually downstream bit rates are pretty high. The upstream bit rates tend to be very, very low. But the problem for satellite communication is actually the end-to-end delay. Because of the distance, of course, because of the communication, the distance to the satellite is very, very long, and the end-to-end delay tends to be very high, 270 milliseconds for an end-to-end packet. This is not counting the delay in the core network. So you get to the satellite just for accessing the internet, and from then you have to go through the internet, which introduces another end-to-end delay, and that's in many cases is not actually feasible, and that's why people stopped using satellite communication for internet access. They use satellite communication, of course, for other applications, but not for internet access. Okay. So network core. So that's it for the part regarding the edge network or the access network. So for access network, we talked about how the end devices can access the internet using residential type of access network or institutional type of access network or a broadband mobile access network. And the different lengths that they can use, physical medium, whether it's guided or unguided. For the core network, so for the core network, we have to move ourselves now to the central office, to the service provider. Okay, so this core network carries now the aggregate traffic from all the access networks, whether it's residential, institutional, whatever. And now the service provider wants to send this data, the aggregate data, across the core network. And the core network now can use enterprise type routers, not like the routers that we use in our houses. They use enterprise type routers, which can support very, very high data rates. In some cases, they use routers that have optical ports, which can support very, very high data rates. Okay. So in that regard, we talk about this core network, and this core network can take one of these two forms, and you need to understand the difference between the two very, 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 very well, because these are fundamentals. I suppose you have come across circuit switching and packet switching before, but these are really like some basic fundamentals that differentiates the different types of services that you can support over this core network just by labeling this network as circuit switched network or packet switched network. Okay, so that's very that's very important to understand. So these networks, we say that these networks are interconnected, meshed together, okay, and they can form circuit switching or packet switching. So for circuit switching, we talk about dedicated circuit, okay. So for example, when we try to make a call over the landline, okay, the first thing that happens is that we hear a ring. What happens is that your call request is going through the core network, and the core network is trying to create or to establish a circuit for your call end to end. Okay, so this is the first type, the circuit switching. For packet switching, we don't have to establish any virtual circuit. We don't have to establish circuit end to end, which means that if you want to send data, just send. And just to appreciate the difference between the two, for our mobile, we can use two types of services to talk to others using voice call, right? So we can use the mobile network through dialing the number. If we dial the number, we use the circuit switched network, okay, and a virtual circuit will be established for your call, okay. And in that case, we get charged by the minute or by the second, right? Why? Why we get charged by the second? Because whether you are talking or not, you are consuming that circuit. The circuit is dedicated for you. Okay? So I can dial a number and I can leave the phone and not talk. So what am I doing now? I'm wasting the network. Okay? But I'm not gonna fool the service provider because they charge me by the second. So do that and you will be charged for whatever duration of time you're leaving your phone. Okay? So what I'm trying to say is that in circuit switching, whether you are using that circuit or not, you're consuming these resources from the actual network. The core network is dedicated for you. And that's why the service provider charges you by the second or by the minute. Try to do the exact same call using Skype or using WhatsApp or using whatever. So all of a sudden, you're switching to the packet switched network. So will you be charged by the second in that case? What is the charge based on? The amount of data. See the difference now? By the amount of data. Why? Which means that if I do WhatsApp and I talk voice, I make voice call and I leave the phone like this, I'm not going to be charged. Of course, WhatsApp will create like some packets and send it over, even if you are silent, because it doesn't know that you're silent. But I mean, effectively, if you make a call using packet switch network and not use it, you're not consuming any resources from the core network. So you get charged by the amount of data you send to the network. Okay? This is the fundamental difference between the two. So, in other words, for circuit switching, you create virtual dedicated circuits for each session or for each call that you're trying to do. And this circuit will be reserved for you during the entire duration of this call, even if you don't use it. Versus packet switching, what will happen is that you will create, your services will create certain packets, and these packets will flow into the network as they get formed, without dedicating any circuit, without establishing a circuit. So if you generate packets, your packets will flow into the network. If you don't generate packets, then you're not doing anything, and the core network is not giving you any resources. Okay, so let's see the difference. So for circuit switching, the end-to-end resources are reserved for you all the time. So that's why in circuit switching, the first thing you should do is to establish the circuit. It's like you are constructing a pipe, and then you start using it. Once the call ends, you destroy that pipe. Of course, that pipe here is virtual, is logical, is not an actual physical pipe. A pipe here means that there is a specific data rate that gets guaranteed on every single router that the call passes through. And this virtual circuit will be dedicated and established. Once the call ends, all this circuit will get dismantled. Okay? So in that case, what we need to do at the beginning is to first establish the circuit. And that's one of the disadvantages of circuit switching, is that you have to establish the circuit first. And sometimes this circuit establishment takes seconds. So first you have to create the circuit, then you start sending information. Because what happens is that once you create that circuit, you have a guaranteed quality of service. Why? Because you have a guarantee whatever you will send, it will get to the other side in a specific time and in a specific order. It's like a pipe. It's like an actual pipe. When you send something sequentially from one side, it gets to the other end in a specific time and in a specific order. You cannot send two packets and they arrive out of order. It doesn't happen because you have a circuit that's dedicated for you. مفهومة كده؟ Okay, so that's easy. So in that case, you have a guaranteed performance, and this is the exact same reason that they built public switch telephone network based on this concept. You almost never, I mean, in the past, you almost never, call someone, and your voice gets cut off in the middle of the communication, unless there's some problem in the switch or something like this. Why? Because all the switches are now dedicating a specific amount of resources for your call. And again, maybe you didn't live that time, but in the past, in some cases, if you have, like when we tried مثلا from North America to call مثلا Egypt or to call the region during Eid time مثلا, you're like, all circuits are busy now, please call again later. Right? Of course, we don't hear that message nowadays, but we used to actually get this message sometimes. Why? Because I'm trying to establish the circuit, and some of the switches on the way tells me that I don't have resources for you. So if you cannot reserve the resources, you will not start the call. Because guess what? Once you start the call, you have to guarantee that these resources are dedicated. مفهوم? And that's why once the circuit is established, you have guaranteed performance. You listen to the voice, and the voice has the same quality throughout the entire duration. Versus if you try مثلا Skype, sometimes in Skype, you get the call, it gets distracted, you get pauses, why? Because it uses packet switching. So for packet switching, you don't have any dedicated circuits, which we'll talk about. So network resources are divided into pieces. For circuit switching, the network resources will be divided into pieces, and these pieces gets allocated to each circuit. For example, virtual circuit can be divided, like I divide the whole frequency into channels and allocate certain channel to a certain user. So this way I'm creating a virtual circuit which is different frequency ranges. Or I can divide the time, as we will see. But I have to divide the resources into pieces and then allocate pieces to the user. And the bad thing here is this. These pieces or these resources cannot be shared. Once I dedicate these pieces for you, even if you are not using it, خلاص, they get wasted. That's when I tried to explain when I said that you can make a call and then leave the phone without talking or without initiating any conversation. You're wasting the bandwidth because you have resources dedicated for you and you're not using them. That's the bad thing about circuit switching. So dividing the link bandwidth can be done in the frequency division or can be in the time division, which is what we call frequency division multiplexing or time division multiplexing. Are you familiar with these terms? So basically, this is how it looks like. So we said that the physical line itself has specific frequency characteristics, right? So for example, a telephone line can support frequencies from 0 hertz all the way to مثلا 1 megahertz or something like this. So I get this 1 megahertz and then I divide it into different channels. Let's say I divide the 1 megahertz into 4 channels. This means that this line can support 4 circuits, which means that this particular link can be used by 4 users concurrently at the same time. If there are more than 4 users, tough luck. خلاص ما في. I cannot accommodate your call. Of course, if you want to accommodate more number of users, you have to divide the bandwidth into smaller frequency. Or you can divide that same bandwidth into time durations. So you divide it into 4 time slots. You say this slot will be dedicated to user or to circuit number 0. This will be dedicated to circuit number 1, 2, and 3. And then you recycle. This is 0, 1, 2, 3. You recycle 0, 1, 2, 3. So during that duration of time, circuit 0 can use the entire bandwidth for itself, can use the 1 megahertz, but in a short amount of time. Okay? So this is what we mean by dividing the network resources into pieces. So the network resources can be divided either in the frequency domain or in the time domain. Okay? Or in a it can be both طبعا. It can be both, like GSM مثلا. GSM divides the channel into frequency ranges and time slots. So so the channel will be something like this. So this is time and this is frequency. So you have frequency ranges and you have time slots. Okay? So in which case, if your frame ends here, how many users you can support in this frame? Yeah? You have 4 4 time slots and 4 frequency ranges.
So it's
Hmm? ها؟
no, it's 5 here.
وفين 5 جت منين؟ 16 يعني 4 هم 4 by 4. لا هو ده بس ده مش okay. 4 by 4 يعني 16 users. Okay, and then in another frame you can support 16 users and so on. So you can divide your channel resources in any way you see appropriate and dedicate specific resource to a specific user. So this way you can create virtual circuits. And virtual circuits, as I said, guarantees the performance. And that's, but the problem here is that I assign this to a user and the user does not have anything to send. Okay, so this one is wasted. So in one frame you can end up wasting some of these resources, and that's why the service provider charges you by the time, not by the amount of data you send. For packets with one is that I had to spend an overhead of 500 milliseconds at the beginning to establish, which is something I don't have to do if I were to use packet switching. I don't have to establish a circuit. The other thing is that depending on whether I'm using the slot that's allocated to me, whether the other users are using the other slots or not, these slots might be wasted. So I increase the time for myself, and I'm not using these resources for any other users. Okay. If I don't do this in the case of packet switching, if I send packets, then I'm consuming the entire bandwidth for myself. If I don't send packets, and if other users are sending packets, then our packets will get interleaved and they will share the entire bandwidth. If 2 users are sending, they will share the bandwidth amongst 2 users. If 3 are sending, the bandwidth will be divided amongst the 3 users. If 4, automatically. I don't have to reserve resources beforehand. Which means بقى ايه بالعربي كده انت وحظك يعني. So because for packet switching, if 2 users are sending, well, each of them will get reasonable data rates, right? If 3 users are sending, the rate per user will decrease. If 1,000 users are sending at the same time, there is huge amount of congestion. It's like you have a roundabout and everybody is going through. You have traffic jam. So in that case, I don't have any guarantees. You may wait in the line for a few seconds before your traffic passes through. That's the bad thing about packet switching. Okay? So you can think of circuit switching as highway, and I'm going through the highway, and but the problem is that if I don't use the highway is going to be wasted, not utilized. And that's bad from the service provider point of view. Versus roundabout or intersection, well, more people are using the intersection, good. And less people can go faster and faster. But if there is huge amount of traffic at the same time, then you have to wait forever. Okay? Second, okay, to consume another slot here. Okay? So the question is how much I can send during this actual slot.
The amount of bits per second.
Right.
And so we would like to divide it by the time slot.
Right. Right. So the actual thing is that the best way is that forget about dividing the channel now. If I were to use the full bandwidth for myself, okay, how much will be the time I spend to send these bits? How much time do I need to transmit these number of bits?
We define the number of bits by 1 point.
Bravo. This will give me what? The transmission time.
Yeah.
Right. Remember, طبعا, there is a very important assumption here, which is we're neglecting the propagation time across the link. Yani, this transmission time is just for A to send all the 640,000 bits over the line. And we're neglecting the fact that these packets, when they are converted to signals, they get propagate and they have to spend an amount of time. But usually this propagation time is close to the speed of light, which is usually يعني, in the nanoseconds, which we can ignore. Okay? So what we are calculating here is the transmission time. And we will talk in details about this, the difference between propagation time, transmission time, queuing time, processing time. All these are times that the information encounters when it goes from one node to another. Okay? We'll go into this. So, so forget about the 24. So first I have to simply spend 500 milliseconds to establish the circuit plus زي ما قلنا 64,000 over 1.536 times 10 to the power 6. So this is the time I have to spend if I were to use the entire bandwidth for me. But what happens is that only 1 over 24 of this is allocated for me. صح? So I need to divide by 24 or multiply by 24 هنا. Huh? Bravo عليك. So I need to so this time increases 24 times because of the fact that only I'm using 1 over 24 of the bandwidth of this time for myself. Okay? So I have to multiply here by 24. So this is the actual time. Right? Because this time is the time that I transmit all the bits if I use the entire bandwidth for myself. But I'm using this bandwidth, yes, entirely, but in a specific duration. So for every second, I'm using only 1 over 24 of this second. صح? Which potentially means this delay will be multiplied by 24. Okay? مفهوم كده? Okay. So, so there are two things we have to pay attention to here. برضو بيعملها برضو. So packet switching, for packet switching, each end-to-end data stream divided into packets, and user A and B packets share the network resources. There's nothing reserved for you beforehand. Okay? Each packet uses full length bandwidth and resources used as they are needed. I'm not reserving any virtual circuit for you. The good thing about this is that I don't have to establish the circuit. And if you have more packets, you will consume more. If you have less packets, you will consume less. That's good. But the problem, because you are not reserving things beforehand, then you don't have any guarantees. You cannot guarantee the quality. So there's no bandwidth division into pieces. Well, in a way, it happens automatically when you go through the network. But you may actually come across what we call resource contention. If you have very high data rates, if the aggregate traffic exceeds the amount of resources that you have, for example, if you have a router and a huge amount of traffic coming from the users are forming huge amount of traffic, you get some congestion on the router. which will be translated into high wait time. You encounter higher delays. And that's what you encounter when you make a call through Skype, and all of a sudden you see that the call is deteriorating. Is not cutting off, but deteriorating. Because of the notion of what we call store and forward, what happens is that the router will receive the aggregate traffic, will have to store it into a buffer, and then get from this buffer one packet at a time to know where to direct this packet. So this is what we call store and then forward. By the notion of this store and forward, you have to store first, process, and then forward. This takes time. It's like you're getting to the bank, you want to get a service, you have to wait in line. Depending on what time of day you reach the bank, you may find this line very short or very, very, very long. Right? So that's the variable time end-to-end that you encounter. And that's what we call queuing time. So inside the router, when you have multiple users like A and B are trying to send, we say that these packets are multiplexed. So you get packets from A and packets from B. They are interleaved like this. And as you can see, this interleaving might be uneven. Because here, clearly, A has more data than B. You have 3 packets from A and 1 packet from B, which indicates implicitly that A has more data than B. And that's the good thing about packet switching. Because in circuit switching, what will happen then is that these 3 packets will have to wait for 3 different frames. And B will use one of these 3 frames and the other 2 frames will be wasted. Because I have to be fair to all the users. I give the same amount of resources to each user. But here, all the packets are multiplexed together and they are sent over the same line. As you can see, there is clear indication that A is sending more data than B, and the packet switching will behave efficiently in that case. And there are some silence periods, and in that case, of course, the network is not being utilized, but there's no user sending. What can I do? I mean, none of the users are sending. So what can I do? Okay. So inside the router, I will have to queue these packets, and then this is what we call store and forward. So from the storage, I get 1 packet at a time, and each packet I have to process it. What does the router do to process the packet? I'm just asking questions just to make sure that you are awake, huh? Analyze it. What does it do exactly? To check the A? Check the IP address inside this packet. Because I need to send or route these packets accordingly. It's like you are going to an intersection, right? You want to go this direction or this direction. You want to go left or you want to go straight or you want to go right. So that's what the router does. It needs to know whether to send it right, left, or straight, or okay. So what information does it need in order to know this? The IP address. So it checks the IP address in the packet, and based on that, it decides to forward the packet on some specific port. Okay? So this processing takes time. This processing takes time because I might have to consult a lookup table, routing table, and I have to do some processing. Okay? So this wait time, if the traffic is too high, this wait time might cause some traffic congestion, and these packets tend to wait for a very long time inside the router. So here, the main thing is that the A and B do not have a specific sequence or a specific resources assigned to them. Versus TDMA or TDM, time division multiplexing, where in that case, each host will have a specific time slot, and these time slots will have to circulate, in which case B might not have data to fill all these time slots, in which cases these time slots will be wasted. So this is you will have to stop here because this requires some probability calculation, and I don't think you are in the phase of following this by any chance. I think you are.